welcome to another module in this massive open online course on Bayesian MMSE estimation for wireless communication systems. Alright, so far we have looked at the principle of MMSE estimation when the observation is Gaussian and the parameter is Gaussian, alright, and we have looked at two applications of this principle in the context of one for a wireless sensor network, two for the wireless channel estimation problem, alright. So now what we are going to do, let us complete this analysis by also looking at the mean squared error of estimation, okay. So what we are going to do, we haven't discussed this so far, we are going to look at the MSE of estimation, or this is the mean squared error. MSE stands for the mean squared error. The mean squared error of estimation, correct. For the parameter h, we know that the MSE is defined as the MSE, the mean squared error is defined as the expected value, this is the mean of h hat minus h whole square, correct. H hat minus h whole square, this is naturally, this is the squared error, where h hat, remember h hat is the estimate, correct, h is the underlying true parameter. So, we are looking at the error which is h hat minus h, we are looking at the squared error which is h hat minus h square, and then we are taking the expected value, correct, the expectation operator, which gives us the average value of the squared error, which is nothing but the mean squared error, okay. So, this is basically your squared error, and once you take the expected value together with the expected value, this becomes your mean squared error, and this is an important parameter, correct. When we talk about the MMSE estimation, or when we talk about any estimation, when we want to characterize the quality of the estimate or how accurate the estimate is, alright. So, we have to characterize it in terms of the mean squared error of estimation, okay. And we have also derived an expression of this, the mean squared error of estimation for the MMSE estimate. We have shown that this is equal to RHH, the mean squared error of estimation, this is equal to RHH minus RHY into RYY inverse into RYH, okay. In our case, this will also be given as, alright. So, this is the general expression for the mean squared error of estimation. For instance, let us consider, for instance, this is the covariance of H cross covariance of H comma Y, and this is the covariance of Y or covariance matrix, depends on Y is a vector or a single scalar quantity. For our case, this is the covariance of Y, okay. So, depends on the nature of Y, if Y is a vector, then this is going to be a covariance matrix, otherwise if Y is scalar, this is simply the covariance, okay. This is the expression for the mean squared error, okay. So, this is the expression for your MSE, alright. We have derived this expression, in fact, we have derived this expression for the scalar scenario, the vector scenario, and so on, okay. Now, let us look at this in the context of our wireless sensor network. Let us go back to our example of the wireless sensor network. Let us look at it in the context of wireless sensor network. Remember, in the wireless sensor network, we are considering a scenario with n sensors, sensor I or sensor K sends the measurement y of k this is the measurement okay, this is the measurement y of k, correct. And what we have is basically we have n such measurements, therefore, what we have is we have y 1 equals h plus v 1, y 2 equals h plus v 2, so on y n equals h plus v n. These are the n observations, correct. These are your n observations. These are the, this is the parameter, h is the parameter of interest. H is a parameter, these v 1, v 2, v n, these are the Gaussian noise samples. And we have also shown that this system model, this setup can be represented as y bar equals 1 bar, the vector 1 bar times h, the parameter h plus v bar, where v bar is the noise vector. So, I can write this as y bar equals vector 1 bar times h plus v bar, where y bar equals y 1, y 2, so on up to y n. This is the observation vector. 1 bar is the vector of all ones h plus v bar is v 1 v 2 up to v n. So, this is your vector y bar, this is your vector 1 bar, this is your vector v bar, which is the noise vector. Okay. This is our WSN system model, this is our estimation model for WSN, this is our estimation model . This is our wireless sensor network estimation model, the estimation model for the wireless sensor network. Now, what we want to do, okay, we have already computed the MMSE estimate. So, the MMSE estimate h hat for this scenario, that is what we have already seen. We have already seen the MMSE estimate, and in fact, we have also seen an example of how to calculate this MMSE estimate for a simple example, all right. Now, what we are going to do, we are going to calculate the MSE, that is a mean squared error for this wireless sensor network estimation scenario, all right. So, now we know for this scenario, the mean squared error will be calculated as follows: RHH, we know this quantity is basically expected value of h minus mu h square, this is equal to sigma square. And more importantly, you remember we said we assumed h to be Gaussian with mean mu h variance. So, h, the prior distribution, what is this? This is the prior distribution of h, all right. This is the prior distribution of the parameter h, where the parameter h is assumed to be Gaussian with mean mu h and variance sigma h square. Okay. And therefore, RHH is expected value of h minus mu h square, which is sigma h square. Further, we have r bar h y, this is going to be a vector, this is going to be expected value of h minus mu h into y bar minus mu bar y transpose. We have already evaluated this quantity r bar h y. This is going to be sigma h square into 1 bar transpose sigma h square into 1 bar okay. This is going to be sigma h square into 1 bar transpose, that is it. This r h y is expected value of h minus mu h into y bar minus mu y bar, this is sigma h square into 1 bar transpose, and you can also see this is r bar y h transpose, because y h transpose is expected value of y minus mu bar y into h minus mu h, okay. And you can see this quantity r bar h y is r bar y h, this quantity r bar h y is nothing but the transpose of this quantity r bar y h, okay. So, these two quantities are basically transpose of each other, that is what you can see, these two quantities are transpose of these two quantities are basically the transpose. R bar h y is the transpose of r bar y h, that is r bar h y is r bar y h transpose, okay. And in fact, r bar y h is a column vector, because it is expected value of y bar minus mu y bar, which is a column, times the scalar h minus mu h is a column. R h y, which is expected value of h minus mu h times y bar minus mu bar y transpose, where y bar minus mu bar y transpose is a row vector, all right. So, the r bar h y is going to be a row vector, okay. So, this you can see, again you can check all these things, this is going to be a row vector and r bar y h, this is a column vector, okay. Now, what we are going to do, therefore, and we have one more quantity, remember the covariance of y r y y, this is going to be a matrix, this is going to be expected value of y bar minus mu bar y into y bar minus mu bar y transpose, which is going to be, which we already derived as sigma h square 1 bar transpose plus sigma square times identity. What is this quantity? This quantity is the covariance matrix. This quantity is the covariance matrix of the observation vector y bar. Okay. So, what we have? So, now we have all the ingredients of this. We have the variance of h, we have the cross covariance of h comma y, and we have the covariance matrix of y bar. Okay. And so, now we are going to substitute this and derive the expression for the MSE. So, the MSE is basically given as expected value of h hat minus h whole square equals, what is that? We have already said that is r h h minus r bar h y into the covariance matrix r y y inverse times r bar y h, which is r bar h y transpose. So, this I can write this as sigma h square minus r bar h y, which is basically sigma h square 1 bar transpose times sigma h square 1 bar transpose plus sigma square identity inverse times 1 bar into sigma h square. Okay. And now, this is your r h h, that is your sigma h square, this is your r bar h y this is your R y y inverse, correct, and this quantity is basically your R bar y into h. Okay. So, now we have this expression which is basically your sigma h square minus sigma h square 1 bar transpose into sigma h square 1 bar transpose plus sigma square identity inverse into 1 bar times sigma h square. Now, what we want to do? We want to simplify this expression for the MSE further, and to simplify this expression further, we are going to use a result that we already seen before, that is this quantity. Remember, we have seen already before, and you can refer to the lecture on estimation in the wireless sensor network, that is sigma h square 1 bar transpose sigma h square 1 bar transpose plus sigma square identity inverse. We have seen that this quantity is nothing but this quantity is equal to this quantity is equal to sigma h square 1 bar transpose 1 bar plus sigma square inverse times sigma h square 1 bar transpose. And in fact, we also know that this quantity, the sigma h square 1 bar transpose 1 bar plus sigma square, this is a scalar. In fact, therefore, this quantity is a scalar, correct, because 1 bar transpose 1 bar is a transpose is a row vector, 1 bar is a column vector, 1 bar transpose 1 bar is n. So, this quantity is a scalar. In fact, its inverse is also simply going to be its reciprocal, because it is a scalar. Okay. So, this is going to be, what is this, sigma h square 1 bar transpose 1 bar is n plus sigma square inverse times sigma h square into 1 bar transpose, which is sigma h square transpose divided by, well, sigma h square times n plus sigma square. Okay. So, this is the simplification. Now, therefore, we can simplify. Now, we are going to substitute this quantity, let us call this as your star. We are going to substitute, these two are equivalent. So, we are going to take the star here and substitute it above, and therefore, what we have is expected value of the MSE, that is expected value of h hat minus h whole square equals sigma h square minus sigma h square 1 bar transpose divided by sigma h square n plus sigma square into, well, 1 bar times sigma h square. Now, look at this 1 bar transpose into 1 bar, this is basically equal to n. Okay. So, now therefore, what I am going to have is finally sigma h square minus n into sigma h raised to the power of 4 divided by sigma h square n plus sigma square, and this is further equal to, now look at this, sigma h square into sigma h square n. So, this is n, once you simplify, n sigma h 4 plus sigma h square minus n sigma h raised to the power of 4 divided by sigma h square n plus sigma square. Now, this is equal to, well, these two obviously cancel. So, what you have is sigma h square times sigma square divided by sigma h square n plus sigma square. Now, if we divide both numerator and denominator by this quantity sigma h square sigma square, we are going to divide, to simplify further, we are going to divide the numerator and denominator by this quantity sigma h square times sigma square. So, this is your MSE, and now divide we have the MSC can be equivalent to divided. Of course, once you divide numerator by sigma h square, you have 1 in the numerator divided by dividing sigma h square n by sigma h square sigma n square sigma square. So, you have n divided by sigma square plus sigma square divided by sigma square sigma h square. This is sigma h square, and therefore, what you have is now just one final modification. This is 1 divided by 1 over sigma square by n plus 1 over sigma h square. And now, if you look at this, what is this? This is basically the MSE. Let us first write this down. This is the mean squared error expression for the mean squared error, basically which is defined as expected value of h hat minus h whole square. And now, more importantly, if you look at this, okay, this is the mean squared error expected value of h hat minus h whole square. And now, we have an interesting interpretation of this. Look at this again, look at this quantity. You can recall that this quantity sigma square divided by n, this quantity is the mean squared error of the ML estimate. Correct? We have seen that already during the estimation in the wireless sensor network, that sigma square over n, if there are n measurements and sigma square is the variance of the additive white Gaussian noise, then sigma square over n is the MSE of the ML estimate, and where ML stands for the maximum likelihood. Okay, so, ML stands for the maximum likelihood. Okay. Similarly, sigma h square is the prior variance. Okay. Therefore, what we have is the MSE is basically, you can now see that this is nothing but 1 over the MSE of ML mean squared error of ML plus 1 over variance of the prior, and this is an interesting result, which basically means that, look at this is nothing but the harmonic mean. So, this is basically harmonic mean of MSE of ML and variance of harmonic mean of MSE, the mean squared error of the ML estimate, harmonic mean of the mean squared harmonic mean of the MSE of the maximum likelihood estimate, and the variance of the prior. And you know from the property of the harmonic mean that it is less than both. The harmonic mean of two quantities A and B is less than both A and less than B. Therefore, this variance of the MSE, the MSE of the MMSE estimate, the minimum mean the mean squared error of the MMSE estimate is less than both the MSE of the maximum likelihood estimate and also the prior variance. Okay, and that is naturally because you have some prior information, you have the maximum likelihood estimate that you obtain from the samples, and you are combining these two. All right, so you are using the information from both the observations and also the prior. Therefore, you expect the net error to be lower than the individual errors, and that is an interesting observation that you have over here. Okay, so the MSE, so this MSE, remember, is less than both MSE, harmonic mean of both is less than MSE of ML and In fact, you can say if MSE of ML is very small, let us look at this. If, now look at this, the MSE equals 1 over sigma square by n plus 1 over sigma h square. Now, if sigma square over n is much smaller, all right, let us say MSE of ML is much smaller than sigma h square, then we can see that 1 over sigma square over n is much larger than 1 over sigma h square. Therefore, this will be approximately, in this scenario, this will be approximately equal to 1 over simply 1 over sigma square over n, all right, which is basically simply sigma square over n equals MSE of the maximum likelihood estimate. On the other hand, if for other scenario, if the prior variance sigma h square is much less than sigma square over n, then 1 over sigma h square is much greater than 1 over sigma square over n. So, this first term, which will be this term, will be dominating in this scenario 1 over. So, MSE will be approximately equal to, so MSE is approximately simply equal to 1 over sigma h square, which is equal to sigma h square. And this is also intuitive, because what this means is basically the ML variance is much smaller and the prior variance is larger. It means that the ML estimate is very accurate. So, you can simply look at the ML estimate, and in this scenario the net variance will be the ML variance. On the other hand, if the prior variance is very small compared to the ML variance, then it means that the prior information, that is a parameter, is very close to the mean, the prior mean, that is mu h, and the net variance of the estimate is basically close to the prior variance, that is sigma h square. Okay. And for all the other combinations in between, basically it is the harmonic mean of the MSE of the ML estimate and the prior variance. All right, this is an interesting observation that you can see. Let us do a simple example to understand this thing. Okay, similar to the the MMSE estimate, let us do a simple example to understand this. You have our WSN example that we have considered previously. Let us do the same example. We have n equal to 4 sensors. We have n equal to 4 sensors, and we have the measurements x1 equal to 1, x2 equal to 2, x3 equal to 2, and x4 equal to 1. Okay. Noise power, we have the dB noise power equal to minus 3 dB implies 10 log 10 sigma square equals minus 3. This implies sigma square equals 10 to the power of minus 0.3, which is approximately equal to half. Okay. Mu h, let us say the prior mean mu h, this is equal to 3, prior variance sigma h square equals 1 by 4. So, this is the prior mean of the prior, this is the prior variance sigma h square, therefore, the MSE, now we have all the ingredients, MSE, and we have ML, MSE of ML equals sigma square divided by n, that is sigma square is half divided by n is 4. So, this is equal to 1 by 8, and therefore, the MSE, the net MSE equals 1 divided by 1 over sigma square over n plus 1 over sigma h square. All we have to do is substitute the various quantities. So, this will become 1 over sigma square y n is 1 over 8 plus 1 over sigma h square is basically 1 over 4, and this will be 1 over 8 plus 4 equals 1 over 12, and therefore, the MSE, the net MSE equals 1 over 12. Okay. So, this is what we observe, the net error of estimation, mean square error, and you can see clearly this is less than your MSE of ML, which is equal to 1 over 8, and this is also less than sigma h square, which is equal to 1 over 4. So, what you are seeing is, because the MMSE estimate, it combines basically it optimally combines the maximum likelihood estimate and basically the prior mean mu h. Its variance is lower than both the variance, or its mean squared error is lower than both the mean squared error of the ML estimate and also the prior variance. And what you see is, in fact, that is true. What we have observed is this, for a simple example, this MSC it's basically is given as 1 over 12, which is less than the MSC of the ML, which is 1 over 8, and also sigma h square, which is 1 over 4. Okay. So, basically what we have done in this module is we have basically simplified the expression for the mean squared error, okay, and we have illustrated how to compute this mean squared error in the context of a wireless sensor network, and we have shown we have given an very interesting interpretation for this. We have shown that the mean squared error of the MMSE estimate is the harmonic mean of the mean squared error of the ML estimate and the prior variance. Therefore, it is lower than both of them. All right. So, we will stop this module here and we will continue with other aspects in subsequent modules. Thank you very much.